This is lesson 5-6 on Dalton's law. Now, the homework is going to be different for the AP Honors or General. Okay, so for AP or Honors, it's actually written on the paper for AP and Honors. It says to work number part 1, 1 and 2, and part 2, 1, 2, 3, 4, 5, and 1. Now, I think it's going to probably take me 2 videos to do this, so it'll probably be even 2 lessons. We'll see. I don't know if I'll get through all of that, so we'll see by then what today's part, what you can do. Now, for general chemistry, you're only going to do 1, 2A, 3, and 4A. So, in this situation, the general does less the problems than the other guys do because there's some advanced stuff on here. General, you're welcome to look and watch this and see the extra stuff, but I'll let you know when I'm getting into something that's going to be just for the advanced. All right, so let me get my outline here. And actually, the beginning is something that everyone could look at. All right, 5-6 Dalton's law, partial pressure. Now, this is one of the more fun or easier laws of all of them. Think about so far we've had the gas laws of Charles and Boyle and Gay-Lussac, and then of course the combined gas law putting it together. Dalton's law, I'll show you. Well, I won't show it to you yet. I'll do it in a moment. First, I'm going to hold this up in my low-tech stuff to show you. This is called a manometer. Let me see if I can try and get there. A manometer. This is a flask with a valve on it, and inside it there's a tube that is shaped like a U, like this. It's called an open-ended manometer. They put mercury inside this. Now, if you fill it with mercury, then of course, as you see, the level on the left and the right are the same. So right now, you might say that will be opened up. The valve is open, so air can flow in and out, and then air can flow in and out of here as well. So everything's equal. Now, when they put a gas inside it, notice what happens. It changes the manometer. This side goes down and that goes up because the pressure of the gas is filling up not just inside the bulb, but also in the whole tube. Now, the number on there, if I can read that one, it's 220. All right, 220 is how many millimeters high it went. That's actually pretty high. Okay. Now, on this side, it says this gas, it's 150. Let me just check that out for a minute. Oh, okay. This one is it's 150 is a difference. I'll just tell you that. So 220 and 150. Now, what's the point of these two things? I'll show you. Well, atmospheric pressure is hitting the top of that. So we'll just say in the first, the second, or the third one, where is the atmosphere pressure equal to the gas pressure, the gas that's inside the chamber? Well, they're equal on this one, because on this one, inside the level is equal, okay? Where is gas A right here? Is it equal to or less than the atmospheric pressure? And you look at this and you'll see here, this gas A must be greater than atmospheric. The way you would know that is because it's pushing up on the, it's pushing more gas and pushing downward on this side and upward there. So gas A is greater than atmospheric pressure here. But down here, gas B's pressure is less than atmospheric pressure. So to calculate them, you're just going to either subtract or add. Now, what I'm telling you right now is an interesting thing just of interest for general, but I'm not really, you can do that if you want to, general, but you can skip past this if you want to. I'll just show you. So the way it works out is the pressure of gas A, okay, we know that atmospheric pressure is equal to 760 millimeter mercury. That's standard. We're going to assume it's standard. Okay, I should have, oh no, it's written on there. If atmospheric pressure equals 760, what would gas A be and gas B? So gas A, we know, is greater than atmospheric pressure because it's like a tug of war in reverse, like a pushing. Gas A is pushing harder than the atmospheric pressure is pushing. So to get the pressure of that, you'll just take 760 millimeters of mercury, which is ATM pressure, if you want to, plus the pressure of, what was the difference there? 220 millimeters of mercury. So the total is 980 millimeters of mercury. That's the pressure of gas A. For the pressure of gas B, all you're doing is you're saying, okay, gas B is less than atmospheric pressure. If it's like a push, tug of war, but a push of war, whatever, who's pushing stronger? Atmospheric pressure now. So gas B is less than that. So that would be 760 millimeters of mercury minus the difference you see there, which is 150. And I could probably do that without the calculator too. So 610 millimeters of mercury would be the pressure of gas B. Get that right? So 760. Yeah, I think I did that right. 79. Okay. Now, the next thing, it says, what if you were to mix together gas A and gas B in one container that's the same size? Okay. This is where I will, this is where now general chemistry this is where you can chime in on this one if you want to see. Okay, so this is what Dalton's law said. Let's say that we have a container. In this case, it's a flask. We'll just say it's a flask in there, and you can measure the pressure. It could be a pressure gauge, even like you use on a car tire pressure or whatever. And there might be a valve or something on this side. You can measure it there, like they call it a Schrader valve that goes on your bicycle there. But inside this one, if the pressure is 980, that's the pressure of gas A. I'll put PA, 980. The pressure of gas B, it would need to be the same size container. Now, we'll just assume they are. I'm not drawing it too good. The pressure of gas B is 610 millimeters of mercury. All right? So 980 and 610. And here's what it says. Let's just say that we combine them both of those into one container, A plus B. So we put all of gas A, we force it into the same container. I'll just make up a number. Let's just say that this is like, whatever, a 3 liter container, a 3 liter container. You're not going to use the volumes in right here, not yet. And this is also 3 liter. If you force all the air here and all the air there, all the gas into here, and all the gas B into there together, guess what the total pressure will be? What will you do? You're just going to add the numbers. Isn't that easy? That is probably the easiest gas law. Probably you would know, just like if you measure the air in one tire, just say you have you have one tire is full of air, the other tire is halfway full. If you were to take all the air and force it from one tire to the other tire, adding them together, you just add them together. So 980 plus 610 is 1590. A plus pressure of A plus pressure of B. Now what they call this, the partial pressure of gas A. The pressure of all the molecules of A that are in here bumping around is 980. Well, over here, the pressure of A bumping around is also still 980. But the pressure of B is 610. So when you add them together, you get that number 1,580. So here's the easy bottom line is the equation. This will make it even better to remember, easier to see. Dalton's law says this. The total pressure of a gas mixture is equal to the partial pressure of each gas, the sum of the partial pressures of each gas in the mixture. I'll say it again because I just went crazy. The total pressure of a mixture of gases is equal to the sum of the partial pressures of every gas in the mixture. If you wanted to use that little sigma, you've seen that. You don't have to, though, if that scares you. But the sum of all the pressures in the mixture. So the sum of gas A's pressure plus gas B's. And if there is a gas C, etc. That is the gas law of Dalton. And a pretty easy one, because all you got to do is add the numbers. Now, there are many, many, many applications to this one. So much that, like I told you, we might be able to do 2 lessons dealing with this. So, here it goes. I'll start off the first problems. Now, as I'm teaching it, there'll be some stuff that we'll be able to leave out for general. So for general, of course, you need to know this is the law. All right, so now there's something called mole fraction. This is really amazing. I'm going to come back to that in just a moment. Okay, so example A says this. The total pressure of a mixture of two gases, helium and oxygen, is 1.505. That's wrong. I'm going to have to change that. The numbers are mixed up. The total pressure of a mixture of two gases, helium and oxygen, should be 5.98 atmospheres. Total pressure is 5.98 atmosphere. I'll tell you why I know that in a minute, in case you haven't. Okay. The partial pressure of the oxygen is 1.505. P of O2 equals 1.505 atmospheres. What is the pressure? What is the partial pressure of the helium gas in the mixture? Okay, whenever you see a problem like this, the other gas law problems are like, here's the pressure, volume, temperature before, here's the pressure, volume, temperature after. But when you see one that talks about multiple pressures, then you'll know that this is the equation you use. So what we do is we actually customize an equation just for the problem. The total pressure in the gases, we said gas A, B, C. Well, in this one, the gases you have are helium and oxygen. So the total pressure with the pressure of the gas helium, helium gas, and the pressure of the oxygen gas. So this is a little equation that we customize just for our problem. And you'll want to do that on these kind of problems. So if total pressure is 5.98, then we don't know the pressure of the helium gas. Isn't that neat? You can show your friends this and they'll think you're really cool how you can turn the element symbol into a subscript. PO2, the pressure of O2, the pressure of helium. Okay? We'll do that a lot in this chapter, and you'll really think you're really cool when you work these out. Okay? So the pressure of oxygen will be 1.505 atmosphere. In case you have the old unedited version of this worksheet, I know that those numbers are mixed up because you can't add up two pressures and get a number that's smaller. So those were flipped on the paper. But oh well, everything's good here. Okay, now, so to find it, all you do is subtract. One thing I'll say, you want to make sure that your pressures are in the same unit. Like they both need to be in atmosphere, and they are. Or both in millimeter of mercury, or both in torr, or both in kilopascal. If one is in kilopascal and one is atmosphere, change them to the same unit. And I would normally go with atmosphere. Stay with atmosphere. Okay. All right. So, but otherwise, you don't need to change them if they match. So 5.98. Well, you don't have to write it down this way, but minus 1.505 on each side. And it comes out to be 4.48 when you use the box rule. Remember, significant figure box rule. Okay? 4.48 atmosphere is the pressure of the helium gas. Now, guess what? That is all that, for this problem, that's all that General Chem will need to do for this particular problem. But I'm going to say a little bit more for the others, for everybody else, AP and honors. Okay, so here it goes. Number 2 says this. Determine the mole fraction of each gas in the mixture. Okay, now what in the world are we talking about here? Okay, mole fraction is just what it sounds like. What fraction of all the moles of gas is helium, and what fraction is oxygen? Now, the reason why we have this equation is actually due to the work of another scientist named Avogadro, and he comes after this, but it's like I want to combine this in right here with the problems. So here's how it goes. I'll just draw a little diagram for a minute here. We need to say what kind of container it was in, but you have helium and you have oxygen. So it looks like oxygen is 1.505 and helium 4.48. So it looks like you have a lot more pressure, a lot more helium, especially because helium molecules are very small. So if they're in higher pressure, for sure they must be in a lot. Hee 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 hee. Is that funny? Or does that scare you? No, I don't know. Hee hee hee. Okay, it scared me, I guess. Okay, so all the oxygen, all the heliums, there must be a whole lot of heliums with that high pressure, 4.48. But the oxygens, they're bigger and they don't even need as many, but hey, I can do this too. So let's just say you have less oxygen, but there's some oxygen in there too. So the pressure of just the oxygen molecules is 1.505, but the partial pressure of the helium is 4.48. And we know that the total of those is about 5.98. Okay, well, here's a neat thing. And I'm going to, I guess I better write these down to remember. Oh, boy. Okay, so pressure of helium, what do we say it was? 4.48. And the pressure of oxygen is 1.505. And the total pressure, we said, is 5.98. I just got to remember that because I don't have a big enough chalkboard. I'm going to have to erase this to move on. Okay, so the formula or symbol for mole fraction is this. It's a Greek also letter. It's chi. And what you do is mole fraction of gas A, we'll just call it gas A, is equal to the number of moles of gas A divided by the total number of moles. Now, that should make sense. If I know the total number of moles, well, I'll take the moles of gas A divided by the total number of moles, and I'll have the mole fraction, the fraction that is A. Well, thanks to Avogadro, and what's a really cool thing about the gas law chapter is you're going to notice this, that you can measure the amount of gas by its pressure. It's directly proportional. And you know what? We already know this because when you go to measure the air on your tires, in a car, in a bicycle, whatever, we'll see how much air is in the tire, and you say, oh, it's got 30 pounds of pressure, or it's got 35 pounds, or 45, or it's down, oh, it only has 10 pounds of pressure. You better put some air in it. So the pounds measures the gas. How can that be? The pressure measures the gas. This only works for gases, not for liquids and not for solids, but gases, it's exact, perfect as weighing as if you were to weigh the gas particles as well. It's just as significant. Well, thanks to this, because I'm telling you, Avogadro helped us put that together, but thanks to this is also something else is true. The partial pressure of gas A divided by the total pressure is also equal to the mole fraction. Now, I made this little equation. I put it in this form myself. I've never seen this written anywhere else that way. I'm sure someone has done that before, but you might want to memorize that because, like, when it comes to AP exams and stuff, they do give you an equation. I'll show that to you later on. They give it to you, but they don't give it to you exactly in this form. What they do is, I think they do what I better not. I don't want to confuse you with it. But if you look on my paper, I wrote that down. I kind of wrote the other way around. Pressure A over pressure T is NA over NT. But these are always the same. Okay, so let's do the problem now. We're just going all of this just to get to part 2 of the problem. And it says, determine the mole fraction of each gas in the mixture. Okay, so in this mixture, helium and oxygen, find the mole fraction. So first we'll say, to find the mole fraction of the helium gas, it's either the moles of helium over the total moles, or it's the partial pressure of helium, and we'll use that. So I'll write it that way. The partial pressure of the helium divided by the total pressure. So the partial pressure of the helium gas is 4.48 atmospheres. The total pressure is 5.98 atmospheres. So 4.48 divided by 5.98 gives me 0.749 is a fraction. So a mole fraction will be fraction. That's the big thing too. If you're ever asked to find a percent on an AP question or honors, whatever, if I say what's the percent, put a percent. If we say what is the fraction, put a fraction. Okay, that's a fraction. Now, it's true, 0.749 times 100 would give you 74.9%. That's true. You could say, well, 74, almost 75%. 74.9% of all the molecules here are helium. Well, but that wasn't what the question was asking. It's what is the mole fraction? There's some other stuff in more advanced chemistry, and some of it, sadly, we will not do because they eliminated it from AP now. But well, you need to know this. But anyway, okay, we'll move on. Or you need to know mole fraction at least. Okay, now to get mole fraction of oxygen gas, this might sound like a little deja vu, but there's two ways to do it. You can either take the pressure of O2, 1.505, divided by the total, or you can just say 1, I was going to have to give it away to you, 1 minus 0.749. Okay, because remember, if you know the percentages of two things, like I told you, one is about 75%. That means the other one, oxygen, must be about 25%. 75% plus 25% gives you 100. If it were percentages, they have to all add to 100. Well, if it's a fraction, a mole fraction, they all have to add to 1. 0.749 plus whatever the fraction of oxygen is must be 1, since there's only 2 gases in the mixture. Now, if you have 3, then you have to, you would have to do it the other way. But 1 minus 0.749 gives you 0.251. And if you wanted to do it the other way, oxygen 1.505 divided by 5.98 is 0.251, almost 0.252, but it's close. And that's a good way to check your work. All right, so that's the mole fraction of helium and oxygen. Then it says this, number 3, if there is known to be 5 moles of gas in this mixture. Okay, we know there are 5 moles of gas in the mixture. How many moles of oxygen are in the mixture? Okay, well, if there are 5 total moles, and I want to find out how many moles of that is oxygen, we're to say that if all this adds up to 5 moles, how many moles is oxygen? Well, you just take the total moles times the fraction that was on, times 0.251, and that's it, okay? Now, that sounds pretty easy. If you want to, though, since I have made this little equation, since we know the mole fraction of oxygen is 0.251, and the mole fraction of, helium is 0.749, well, look at what you can do with my little equation, my handy little equation for you right there. So we can say, well, we know, I'll use this one to do number 3. You can just multiply them. You don't have to do it with this equation, but if you like the equations, there it is. The mole fraction of oxygen, we know, would equal the total moles, the moles of oxygen divided by the total moles. So, if the mole fraction of oxygen is 0.251, then the number of moles of oxygen, I'll put in the total moles down here, which was 5. The moles of oxygen divided by 5 should equal 0.251. That's what I was trying to say. I didn't really come out, but I wrote it right. So then you just cross multiply it. In fact, I guess I will show the cross multiplying. So if I multiply this by 5, then I multiply that by 5. And look, I'm doing what I just said in the very beginning. I just said, well, if I know your total moles is 5, then the fraction of oxygen, 0.251. 0.251 times 5 will give you the moles of oxygen. So you don't have to use this equation, but that equation pretty much does everything for you. 5 times 0.251. It shows you what to do. It shows you a kind of an organized way for it. So 1.26 moles of oxygen would be there in the mixture. Okay. All right. And then, of course, the rest of it would be helium, which would be, you could take 5 minus that. Did we ask that? No, I guess we didn't. But we don't have to do that part. 3.74. Yeah. I was just double checking all the numbers there. So you can get helium 2 ways, by either multiplying the fraction times the total moles, or by taking 5 moles total minus that. Okay. All right. So this is little relationships that are good to be aware of. Now, okay, here's another problem. A balloon contains 2 moles of hydrogen gas and let's see, a balloon contains 2 moles of hydrogen gas and 0.50 moles of oxygen gas at a pressure of 750 millimeters of mercury. Find the mole fraction of each gas in the mixture. Well, now that you know that, this will become pretty easy, I think. Now that you know the equation here. Okay, so 2 moles of hydrogen and 0.50 moles of oxygen. And we're giving you the total pressure. So, find the mole fraction of each gas. So first let's just find the mole fraction of, how about oxygen? It says hydrogen and oxygen. So the mole fraction of oxygen will equal the moles of oxygen over the total moles. Now we know the total moles will be the moles of oxygen plus the moles of hydrogen, H2. So I'm going to change the formula like that a little bit. So that moles of oxygen, if I plug them in right, 0.50. Okay, and the moles, okay, so it goes there and it goes there. And then the moles of hydrogen are 2 moles. Okay. So there's your the math for that. So 0.50 divided by 2.50. So that looks like what? 1/5, right? So 0.50 divided by 2.50, 0.2, 20, yeah, 20, 2 sig figs. I know I put that word there, but then I was realizing I got to do another one below it. So 0.20 will be the mole fraction of oxygen. So you put, since you had 2 gases, you have to add those up. So I kind of did it in one step there. Again, based on something that we used to do, we don't do it anymore. It's a chapter that comes later on. I like to write it that way. It's kind of good because when you go to college, if you take chemistry, you'll see what I mean. You'll get to another section. It might pop up in this class too, something where you had to do this again in the future. Okay, and then, it says each gas. So that's the oxygen. So the hydrogen mole fraction, you can just take 1 minus 0.20. And notice I put 1, last time I put 1.000, this time I can put 2 O's. So your 1 will be a perfect 1. So you can have as many sig figs as this has. So it can have 2 after the decimal. And minus 0.20, so 0.80 would be the answer. And then number 2 says find the partial pressure of each gas in the mixture. So find the pressure of look at this part of the equation, and that will do it for you. Okay, so if oxygen is 0.20, and let me erase this stuff over here. That's the old problem. If oxygen is 0.20, and what was the other? Hydrogen is 0.80. So let's just use that equation and find that. Wow, we're doing a lot of stuff here, and I just realized that I'm probably going to have to change this video and just tell General to not even watch this video because I don't know. You'll see they'll resume in the next video. So I think that's what I'll do. You might, AP and Honors, I think you're the only ones that's going to ever see this video. But next lesson, I might review Dalton's law, and then we'll go into the other stuff. I think that's what I'm going to have to do. All right, so well, we'll see. I can decide about it. But all right, find the partial pressure of each gas in the mixture. All right, since they told you that the total pressure is 750 millimeters of mercury, and now you know the fractions, you can find it out. So remember, mole fraction is equal to the pressure of, we'll just pick a gas. Let's pick hydrogen gas. The pressure of hydrogen over the total pressure. I don't want to say A, but mole fraction of hydrogen. Yeah. Mole fraction of hydrogen is the pressure of hydrogen over the pressure total. So the mole fraction of hydrogen we said was 0.80. So let's plug that in. That will equal the pressure of hydrogen over the total pressure, which was given to be 750. I guess a lot of people would just say, well, just 750 times 0.80 is the answer. And that is exactly what it is. But I just think, I don't know, some of you might like that little equation to kind of remind you of it. But at 0.80 times 750, and it's 0.80 times 7, 150. Is 600. Yeah, okay, so 600 millimeters of mercury, yeah. For a minute, my mind was like, well, 600, that's really, really high. Well, yeah, 750, it's almost standard pressure, so yeah, that makes sense. Most of that should be hydrogen. And then you can even tell, so the pressure of oxygen must be the rest of it. So it should be 150. So you can either take 0.20 times 750 and get 150, or you can just say the pressure of oxygen will equal 750, which is your total. I mean, if you want to write that, minus 600, which is 150 millimeters of mercury. Now I'm putting a little dot after it because it has the sig figs will count there. Okay. Okay. So are we there yet? I've got one more problem to show you, and then that'll be all for this section. And the part about collecting gas over water, I'll have to do a different lesson because it gets to be a little bit, there's more stuff there. So I want to, and probably, like I told you, I'll have to, well, I don't know. I'll see. I might just edit this video and just show the part they need. But they do need the next lesson, but then the next it's going to also go. Okay, I'm just talking to myself here. Okay, here we go. All right, here's a big one. Okay, the two flasks below are connected together by glass tubing. So you have flask A and flask B. And there's a tube, so usually there'll be some, well, I'll just put a tube coming out of this. Oh well, it's kind of weird, but oh well. And we normally put a very thin tube, so we kind of ignore the volume of that tube. Now I'm drawing it in the picture, it looks kind of big, but it should be a real thin, like a real thin straw or something. And these should be much larger. Okay, now there's a valve in between them with a little, you could turn this little knob called a stopcock right here. You can open and close it to let one side, the other side, one gas flow from one to the other. This side is 5 liters. This side, the volume is 2 liters. So this should be smaller. I guess I better do that because I don't want you to get misled by that too much. Liter is the volume, and the volume of a gas, as you'll see later on, the volume of a gas is. We record the volume of the container that it has to move around in. So here's a 2-liter container, here's a 5-liter container. Inside this, so we have 2 liters of nitrogen on this side. See, they're blocked off. And we have 5 liters of helium on this side. And 0.200 atmosphere is the pressure of this side. So let's say if I have a gauge also just for this side, like a little valve gauge, this is 0.200. The pressure on this side is 0.600. So, in this half, 2 liters and 0.600 atmosphere. Now, there will be gas here, and it will even be throughout the tube. But normally on these problems, we say disregard the volume of the tube. But there is gas in that tube, and anywhere that, if you were to measure like air gauge, the pressure, it's always 0.600 all around. Okay, that's your pressure. On this side, it's going to be 5 liters, this container, and 0.200. Okay, so question A says, calculate the partial pressure of the helium gas after the valve is open. So after we open, what will the pressure of helium change to? Now, think about that for a minute. Why would it change at all? Here I've got helium gas. Ignore the other gas for a minute. But if I open that valve, why will the gas change? Okay, because you open the valve, and now all this gas is going to it was trapped on this side, now it's going to flow to the other side, and it will be in homogeneously. It means equally distributed. So like, you might have over here, like, just say you have 100 molecules of helium, okay? What would that be? This side is 5 liters. Okay, well, what's going to happen is when you open it up, you're getting a bigger volume. So now you're not going to have 100 here anymore. A lot of them are going to leave and go over this way. But you'll have an equal amount of particles, like per liter, for example. You have the same number of particles per liter throughout the whole thing. It's always going to be equally distributed. Okay, so how do you figure this out? one thing you do is you use one of the gas laws. And you might not see it right off, but the gas law that can be used here, think about it. We know the volume and we know the pressure before we open this up. So one hint I'll tell you, let's forget about the other gas for a minute. We know the volume and the pressure before we open it. So when I open it up, what will be the new volume and the new pressure? Whose gas law is that? And what do we not have there? We don't have the temperature, because the temperature would be the same. It's not going to change when one goes to another. If it did change, like if there were like friction for a moment, you could just wait a few minutes and then it will be adjusted. It will be back to the same temperature as the room. So, okay, it looks like Boyle's law. So, P1 times V1 equals P2 times V2. Now, since I'm dealing with only hydrogen gas here, helium gas, I'm going to do this. I can say, well, that might get to be too much. I was going to write pressure of helium 1 times volume helium 1. Well, I'll just do this. For helium, I'll just write this. Helium P1 V1 equals P2 V2. So P1 V1, 0.200 is the original pressure. The original volume is 5 liters. The final pressure we don't know, but we do know the final volume, because this side is 5, this side is 2. So when you open it up, the final volume is going to be 5 plus 2 liters, which is 7. Okay, so 7 liters. I'll just do that to make it easier there. All right, so 0.2 times 5 is P times 7. So 0.2 times 5 is 1 equals 7P. So divide both sides by 7. And 1 divided by 7 is 0.143. Pressure of, was it helium? Well, the final pressure. I'll put P2. I'm sorry. I should have left P2 there. I didn't mean to do that. P2. Okay, just to help you. So P2, and I'm going to put helium. So the final pressure of helium is 0.143. Okay. What is the partial pressure? That was letter A. What is the partial pressure of helium after the valve has been opened? It's going to be 0.143. Oh, yeah, that did fit on there. Can you read? I'm trying to, I know I'm trying to squint, but it's so small there. But there it is. Yeah, you can see 0.143. Okay, now, what about B? Calculate the partial pressure of the nitrogen gas after the valve is open. Pressure of helium was 0.143. Looks like I'm going to have to erase something in a minute. So B, now let's find the pressure of the nitrogen. Okay, this is going to be easy because it's the same thing. So now it becomes a little bit busy workish kind of stuff. P1 V1 equals P2 V2. But now we're only talking about the nitrogen side. So it was 0.600 atmosphere times 2 was the original volume. The final pressure we don't know, but we know the final volume is going to be 7, like we just saw a moment ago. So 0.2 times 6 is 1.20 equals 7P. So divide that by 7. So 1.20 divided by 7 is 0.171. You know, I knew there was something kind of weird about that. Put the unit, atmosphere. I forgot to put my unit there. And for P2, yeah. Okay, so your final pressure of the nitrogen should be 0.171. That's correct. I was double checking it another way too. Okay, and then the letter C says, what will be the total pressure inside after the valve is open? Okay, well then the total pressure, you're just going to add them together, right? Do I need the other part? Oh, okay. No, I'm not going to need that, I don't believe. Okay, so I could probably just do it right here. We're almost done. The total pressure of the mixture of gases is the pressure of the helium gas plus the pressure of the nitrogen gas. Oh, one thing important about Dalton's law, I just remembered that I need to tell you. It says the total pressure of a mixture of gases is equal to the sum of the partial pressure of each gas in the mixture, as long as the gases do not react chemically. So the total pressure, you can say it this way: the total pressure of a mixture of a mixture of inert gases. You could say an inert. Inert means they don't react. Okay, like inertia or whatever. But okay, you don't have to say it that way. Just know that this helium will not react with nitrogen, and not so at all. So that's why it is true. If they do react, well then that can change the pressure. And we're going to see that later on in the chapter for the AP, of course. All right, so helium 0.143 plus nitrogen's final pressure 0.171. So my total is 0.143 plus 0.171, 0.314 atmospheres. Okay. That was the last question for, and it just said, oh no, there is one more. That was C. I mean, I said 4. That was letter C. Okay, and then the last one, D. It says, if the glass connection tube has a volume of 0.20, so if this is 0.20 liters, this tube, how would that affect calculations A and B above? Oh my goodness, and I just erased A and B. Okay. Well, the main thing, A and B above. Okay, the main thing is when you're trying to do a problem, they love to ask a problem like this on AP questions at the end, like, oh, if we said we ignored this, but if we don't ignore it, how will that affect it? Will it make your numbers too large, too small, that kind of thing? So what a good way to do it is to think about the equation we used back there, and what we did was we said the original pressure, well, I guess I can go back to the question and say, for example, let's just say helium. And it'll be the same effect for both of them, for A and B. But let's just actually put numbers and think about that. For helium, we had 5 liters of 0.20, 0.200. Okay? And we found out your final pressure, all right? But what we had to do was your final volume had to be, we said 5 plus 2. But now, if we have to also include that, that actually tells you what to do. We have to also put in 0.20. So, since the volume, that would cause your final volume will be larger than estimated. So remember, so if this is 0.20, that means compared to what we calculated earlier, the final volume would be larger. And if that number is larger, then that means that your pressure will be larger or smaller. Do you know? It'll be smaller. Another way you could also do this, how would it affect your pressure? Okay? P1, V1 divided by V2, that's how we got P2. So how will the pressure change? Since you're going to be dividing this by a larger number, so this is going to be if the bottom number increases, if you're dividing by a larger volume, that is going to cause you to get a lower value for your pressure for A and for B, for both of those gases A and B. So that will be the way you'd answer that. You don't have to always use numbers in that. In fact, you could just answer that, well, how would it affect it? Well, since we ignored it, since we ignored that volume, if we did not ignore the volume, since it would cause the volume to increase, your final volume to increase, it would well, I'm saying it in a weird way. Since it would increase your final volume, your final pressure would be lower. And I would do this. I would like to show an equation like that. I think it's good to write an equation and show that if I increase volume, then your pressure is going to be lower. Okay. Well, all right. Thanks so much. I know it's a long lesson there, but hopefully that'll be good. The work will be pretty easy. I think the math is easy on most of this stuff. I'll see you guys.